about where renewables are going. And RMI is close to my heart because the founder, Amory Lovins, wrote a book in 2011 called Reinventing Fire, which is the single thing that cured my sense of despair about our ability to solve the climate crisis. He really laid out how it could be done and gave me a sense of optimism I didn't have. So I'm very, very grateful to RMI for that, and Amory Lovins in particular. So you can imagine this will be a fairly uplifting set of slides. It's also a very dense set of slides. So I encourage you to look at the pictures and the graphs, and not necessarily spend a lot of energy trying to see the text as it goes by. There's a lot of it. So can I get that? Yeah, okay. So in the slides, you'll be seeing the original slide deck from RMI was 66 slides full of information. That was impossible. I eliminated 2/3 of them, and I still have a lot to do here. So I kept the ones that focused on the speed and the inevitability of the transition to renewables, and I omitted most of the data about other countries and much of the financial stuff. But even so, it's going to be quick. So fundamentally, what we're talking about in these slides is the debate between advocates of fossil fuels and advocates of renewables. And the fundamental questions have to do with which is superior. Will renewable growth be linear, or will it be faster than that? Will there be a learning curve for renewables, or will they stay the same price as they are now? Are there insoluble obstacles to adopting renewables? Are there will the tempo of change be set by the renewables or by the fossil fuels? Will the disruption come quickly or slowly, and how will financial markets respond? You can imagine, given my description of RMI, where these questions come out, but let's look at the arguments here. So what I'd like to do is start with a couple of their early observations. I'm skipping a whole lot of slides here, but a couple things that I thought were worth keeping in. One is that the war in Ukraine has changed the equation for renewables to a large degree. What you see in the graph on the right is a spike in the cost of gas and coal. These are data from Germany, whereas the PV, that's solar and wind, prices continue to decline, and so the advantage of renewables has increased as a result of the war. And what has that done? That means that the decision that you used to have to make if you're a country looking at these options between the cost of renewables versus fossil fuels, between the security that you get from generating your own power versus the cheap way of buying power, and the environmental issues, those are all resolved in favor of renewables as a result of the current situation, particularly in Ukraine. Another early slide in the set that I thought was worth keeping was about jobs. What this slide shows is that jobs in coal and oil and gas will be lost, but there will be gains in many other areas, particularly in power generation, in efficiency improvements, in cars, and in the grid itself. And the yellow data is from the pledges that various countries have already announced, and the green is from what would happen to jobs if we went fully to net zero emissions. So there's lots more jobs in the green revolution than there is than we lose in fossil fuels. This data, by the way, is from the International Energy Agency, which will be the source for a lot of the data in this presentation. Very confusing. The IEA and the EIA both provide data that I'll be mentioning along the way. This is the IEA. So you know this, the cost of everything renewable has been going down. These are 10-year graphs showing the changes. One of the interesting things, and the pink band in the middle is the cost of fossil fuel energy. And so you can see that in recent years, onshore wind, offshore wind, and solar have all reached a level where they're below the cost of fossil fuels. And solar has actually, it started expensive, but it's now the cheapest of the bunch. And as a result, the rate of increase in solar, wind, electric vehicles, and batteries has been on a steep acceleration, an exponential acceleration. And electricity has taken over from fossil fuels as the major carrier of energy. So now more energy travels by wire than by pipe. And you can see that in the graph on the left. The graph on the right shows the situation in China, where that hasn't happened yet. They depend more on coal than they do on electricity for their energy, but as you can see, those are converging, and that will change. Here's an impossible to read slide. At the right, you see the cost of various kinds of energy declining. You see solar, wind, batteries, and then electrolyzers, which are used to generate hydrogen from water. And all of those are declining. The red lines are various people's projections of where the prices would go. The black dots to the left are what prices have actually been in the past, and the blue dots going to the right are what are called learning curve dots. Those are the prices you would get if the prices continued to decline as they have in the past with each doubling of the installed base. And RMI argues that that's the best way to project these things. So all of those things are declining rapidly and steadily. And across the bottom, you see that oil, coal, and gas are not declining. And so obviously the implication is that the renewables will gradually displace those. Here is another graph that that gives some of the same information. So here you see at the left that solar and wind are both below the $50 per megawatt horizontal line there per megawatt hour, showing that solar and wind are less expensive than what fossil fuel was before the war in Ukraine, and even less expensive now. And to the right, you have EV batteries and green hydrogen, both of which were generally more expensive than the equivalent fossil fuel. But with the war and by 2030, they should be less expensive. And so, again, this will help the shift over to renewables. And renewables are much better distributed. The energy that supplies renewables is much better distributed than the petrochemicals are. Here you see a map of the world. The reddish areas are where there's overwhelming amounts of sun compared to the electricity requirement. There are very few areas of the world, just parts of Europe and Japan, where there might be a space limitation on renewables, particularly on solar, that would limit their ability to completely handle their own electricity generation. Everywhere else could certainly do it. So we basically have what we need to do this transformation. On inside the yellow box, you see, okay, the energy can be generated by solar and wind and some other things like maybe tidal and hydro and so forth. We have the carriers for electricity by wire and hydrogen by pipe or ship or whatever, plus storage. And then we have the appropriate applications for electricity to take over the various tasks that are now done by fossil fuels. And there's a huge story in some of that we won't go into here, but basically the case that RMI is making is that we have the tools. And in many sectors, we are at or near a tipping point in terms of cost. We already have reached that with electricity. It's cheaper to generate electricity with renewables than it is with fossil fuels. For cars, we are right at that point where the cost of ownership is such that it's basically break even with electric vehicles versus fossil gasoline vehicles, and that will soon change with buildings, heating and cooling and other building energy requirements. That's almost here, and so on down the line. The last to convert will be the difficult ones, steel, cement, and chemicals, but there are solutions in the works for those as well. And according to this data, those solutions will reach their tipping point by around 2030. And so there are no insoluble barriers. People have said, well, when the grid reaches a certain point, it'll be with renewables, it'll become unstable, or there won't be power at the right times and so forth. Denmark at 60% renewable shows that there's a long way to go before we would hit that. The US is at 11% renewable in our grid right now, and most of that is hydro. So this is these curves that you see here are from a consulting firm Rystad, which is one of the big energy consultants out of Norway. And basically what you're seeing here is the projection of S-curve growth for both solar and wind from a very low base. You can see in 2020, we're talking about level of 1 petawatt hour per year for solar and 2 petawatt hours per year for wind. Whatever those terms mean, it's a very low number. The global demand currently is about 28 petawatt hours per year, so a small part of that is currently solar and wind. But if you believe these curves, we'll get there pretty quickly. Should you believe these curves? Well, there's a lot of information to suggest that other things have grown in this way in the past. The left-hand graph there shows individual products that have grown on an S-curve, ranging from flush toilets to cell phones. And on the right, you see infrastructure that has grown on an S-curve like that: canals, railways, telegraphs, roads, and oil pipelines. So there's reason to believe we could be in for that same kind of growth with renewables. And in fact, fossil fuels grew on that kind of a basis too at one point. They've slowed down now. Also, there's efficiency to think about. So most projections assume that efficiency doesn't change over time. This is one of the things that Avery Lovins, the founder of RMI, has emphasized during his career. There is a lot of potential for efficiency improvement, and year by year it gets better. These curves show the amount of energy used per amount of work done, and you can see every year the requirement declines. That's because efficiency is getting better. The green line is Avery Lovins' prediction basically from 1976, and it's held up pretty well. The blue line is what actually has happened, and the purple line is what Lovins predicted in his book Reinventing Fire. So that continues. We keep getting more efficient, and that's an important part of what will help the renewables too. So what happens when you have this growth of renewables and you have this improvements in efficiency? Well, you save an awful lot of energy in various ways. The brown line at the top indicates what would happen if energy just kept growing the same rate as GDP is anticipated to grow. And you can see it would grow quite steadily, but with efficiency growing, that's the yellow part, it doesn't grow nearly so fast. And you plug in renewables into the equation, and it actually starts dropping because renewables don't have the efficiency losses that fossil fuel generation has. A great deal of the energy going into fossil fuel generation is lost as heat and transmission losses and so forth. And you just don't have that with renewables, or not to the same degree. So the white line kind of between the dark blue and the light blue represents the net energy that you would need. And because you have renewable energy involved, that's the lower light blue, it pushes down fossil fuel demand to near zero. So we're looking at an S-curve growth potentially for solar and wind. This is data from Rystad. The only way that can happen is by pushing down fossil fuels. And that combination of a new thing rising and an old thing dropping is very common. These graphs represent the transition from iron to steel, from sailing ships to steamships, from horses to cars, from gas lights to electric lights, steam to electricity for industrial power, and coal to gas for heating. In every case, you have this kind of exponential growth of the new and the corresponding decline of the old. So that's what RMI is predicting for fossil fuels and for renewables the same way. They figure we're at the peak currently. Basically, we're on a plateau. There will be some ups and downs, and then as renewables really take off, it'll drop off a cliff. This graph's a little hard to read, but fundamentally at the right, what we're seeing is the amount of different kinds of energy that have been added to the system over the years, and recently it's all been renewables that are being added. And it won't, although solar and wind are now only 5% of the total energy supply, they are adding about 1% a year. And therefore, if demand doesn't grow faster than 1% a year, then the only thing that can happen is that fossil fuels will decline, and that growth of renewables will pick up. And we can already see signs of that in what's happening with coal. At the left, you see coal use in the OECD, the advanced economies. The US has dropped even faster, UK faster still. And this is what RMI anticipates for fossil fuels generally. Also, the things that use fossil fuels are in decline. In internal combustion engines, mainly cars, that's the left-hand graph, that's declining. Coal and gas power plants, they're declining, that's the middle one. And the oil and gas upstream investment, that means drilling, that's declining. The investment in that is declining. So all of those things suggest a decline in fossil fuels. And demand in many areas is already in decline. In the EU, it's down 20%, that's at the left. In the US, it's down 10%. And for the world, the industrial fuel consumption is down a bit, not much yet, but that will happen. Personal consumption is still growing worldwide. So what does this mean for the investments, for the investors? Investors worry about peaks, and if we are near a peak or at a peak in fossil fuels, then there's the danger that growth is over and the returns that come from growth are over. So investors want more returns for investments in fossil fuels than they do for investments in renewables, where they see an opportunity ahead. So the upper dashed curve represents the cost of capital, the percent return required to get a loan for offshore oil. The solid line below it is for liquefied natural gas. And these are indications, the growth in these curves, indications that investors are losing interest in those areas. And RMI points out that in the past, investors have fled markets when they sensed a peak, and this was true for U.S. coal, true for U.S. For EU fossil fuel fired electric plants, and true for the oil services industry. And it will presumably be true for oil and gas generally soon. Don't pay attention to the so-called experts who represent the incumbent industries, because they are so often wrong. The IEA, the International Energy Agency, has been under-projecting solar for the last few decades, and the yellow line represents what actually happened. The gray lines are year by year what they projected, and you can see how woefully they have done that. On the other side, on the right-hand side, you see the EIA, which is the U.S. Energy Information Agency, their projections for coal, and they have kept projecting that coal would either grow or stay flat, and it's been dropping consistently, and they continue to make those forecasts. So you can't necessarily go with those incumbent experts. So what do we conclude from all of this? That renewables are growing faster than the fossil fuel incumbents think, that the costs are dropping on a learning curve, and installations growing on an S curve. And in many regions and industries, fossil fuels have peaked. There are no insuperable obstacles. And as investors recognize these trends, they will no longer provide capital, and that will kneecap the fossil fuel industry, basically. So there, very quickly, is the gist of the slides from RMI. If you found something of interest there, or if you're interested in the topics I didn't get into, I encourage you to go look at the full thing. But I did what I could in the time that I had.
George, this
Wonderful.
was absolutely fantastic. I'm going to turn it over to Michelle to take questions from the group and give you a full 15 minutes to speak to questions that came up. Michelle, it's all yours.
Okay, Tom Morgan and then Ted Woolner. Tom Morgan. Oh, Tom Morgan is just giving a clap. Okay, different yellow hand. Ted Woolner, you're up.
Two questions on a super presentation, George. One, you seem to indicate that the intermittency problem isn't so much of a problem. Is that the case? And two, what potential does green hydrogen have, and how soon can it be significantly tapped?
Okay, two great ones, Ted. So from RMI's perspective, battery technology is coming along fast enough and in enough capacity that it will solve the intermittency problem. Also, there's a fair amount of synergy between the different kinds of renewables. So solar and wind tend to have different peak periods, and offshore wind is a very constant sort of source, and so forth. So some of these things are solved in those ways. That's a good question, and we don't really have an answer to that. What was part two, Ted?
That was about how quickly green hydrogen.
Oh, yeah. Green hydrogen, you know, I haven't seen much from RMI on this, but my own take on it is that green hydrogen will be important in certain niche applications, but it won't be important for example, for cars. There are a few applications where it might be significant. It could, for example, be significant in shipping, where ships at sea don't have an easy source of electricity. Could be that it would use hydrogen directly, or could be converted to ammonia and use that, which is somewhat easier to deal with. I think the jury is still way out on hydrogen.
Okay, Mike Burke, then Stu, then
Just make a
Steve.
comment about
George?
hydrogen. Yeah, I just watched a video by Fully Charged, and they had some kind of hydrogen expert there talking about that. And basically, George Alexander, your comments are correct that hydrogen is going to be for niche applications. For instance, those huge off-road trucks when they're digging things and there's not a lot of electricity around. But by and large, the battery technology and everything else has eclipsed what hydrogen was touted to do in the Bush 2 era.
Thank you. All right, Mike Burke, you are next.
First, a quick observation, two quick observations. One, great presentation. Thanks, George. And secondly, it would seem that Lovins gives insufficient notice to the other renewable energy sources, and I'm thinking particularly of geothermal in the West. You know, our newest Kendall affiliate out there is going to be, the electricity will be provided by geothermal, which is quite near the surface and pretty easy to tap into, and will drive their electricity generation. And that's not uncommon throughout many portions of the West and Nevada and so on. The question, though, is this, or not really a question, a comment. Looking at all those graphs, it seems that change is inevitable, but I want to caution that change doesn't occur without catalysts, and we are the catalysts that will determine both the direction and the speed of change. The fossil fuel industry continues to be extraordinarily well funded, and it's going to push back like hell on each step of the way. And we're just going to need to make sure we keep our shoulder to the wheel. That's certainly true. Thanks, Mike.
Okay, Stu White from Hanover.
Thank you, George. I was wondering if I could apply for continuing education credits to my architect.
Sorry about that.
Because I'm behind. But I was really glad. That was classic Lovins thinking. Took me right back to the 1970s, and he's got that same way to make it all work. It's so wonderful to hear it again. And I was really glad to see the emphasis on efficiency towards the end, because some of you might remember Steve Woodbury sent around something a while ago that was saying we've got to electrify, but we have to fundamentally change our buildings. And that is make them more efficient. Because if we just plain electrify the load that we have now, and I pulled this up on my iPhone, thank you, Steve, we would need a plausible path to decarbonization would require 590,000 square kilometers dedicated to wind and solar, which would be about the same size as Connecticut, Illinois, Indiana, Kentucky, Massachusetts, Ohio, Rhode Island, and Tennessee combined. So we must go to work in our buildings. And
Stu, let me put that another way. Every investment we don't make in energy efficiency is a permanent mortgage that we're paying every year.
Oh, good.
Good. All right. Ted Burrows, you are next.
And I think I'm unmuted. Can you hear me okay?
We can hear you.
Okay, excellent presentation. Thanks, George. And I'm curious, no mention of nuclear, in particular, the tantalizing idea of the little modular nuclear things. Is that just too early in development?
Yeah, so what I've seen, there was no mention of it in this presentation, even in the slides I skipped. From what I've seen from RMI, their thinking is that it comes too late. Even if it would work, it will come along at a time when the renewables have gotten so cheap and come so far that there's not a role for it.
Okay. Next up is Alan Lockwood, and you're muted, Alan.
Good morning, everyone. I had a similar question about nuclear energy. My concerns range towards the ease with which it seems to be possible to use nuclear reactors to produce weapons-grade uranium and fissile products, and also problems related to the storage and permanent disposal of spent nuclear fuel. There are a number of scenarios where a suicide bomber in an airplane crashes into one of these ponds next to a place like Indian Point, north of New York City, blows up all of the stored spent fuel rods there, and disperses radionuclides over huge areas of the country that then become uninhabitable.
Yeah, certainly a concern. And you know, I think there are still a lot of problems for the small nuclear reactors, and it remains to be seen whether anything will actually come of that, although there are starting to be some early installations on the road to implementation.
Barbara Smith, you are next.
Yes, just a caution, and I would encourage people to read the very brief book review that I did on The Brilliant Abyss. And that is, there's a real push for collecting these metallic nodules from the deep sea in order to have what we need for the batteries. In the process, we may destroy the sea, which produces more oxygen than any place else. So just a caution. And now you know why we love George. We're very fortunate to have him here.
Thank you, Barb.
Ted Woolner, Oberlin.
Yeah, in reference to what Barbara just said, George, does the Rocky Mountain Institute or RMI have anything to say about the environmental or supply chain, potential supply chain problems involved in, producing batteries among other renewable items?
Yes, not in this set of slides, but there's an acknowledgement that any technology, any energy technology causes environmental problems of some kind. In the case of batteries, the general sense I get from the RMI materials and other sources is that the heavy dependence that we have right now on lithium, on cobalt, and on some of the other specific elements that are used in car batteries today, that will be displaced by other battery technologies that use far more common and less environmentally destructive elements. And those those alternative forms of batteries are coming on strong, particularly for stationary uses for the grid and so forth, and for backup power, where there are a number of promising alternatives there.
All right, then James, you are up.
I just wanted to reiterate, and George touched on it, that there are a number of alternative chemistries being worked on for the stationary batteries. We're aware of one in our local community where a company put on solar panels and realized they needed the battery backups, and it relies on a ferrous chloride flow battery. The first one I've seen on the East Coast. I'm also aware of one being developed in Australia that is zinc bromide. So there are a number of different chemistries being explored, and I don't think that the projections will have to rely solely on lithium.
All right, thank you so much, everyone.